Welcome to this CSIG weekly call. I'm going to hand over to today's speaker, Teodoro Laino from IBM Research. Over to you.
Okay, so hello everybody. Very brief introduction about myself. So my name is Teodoro Laino. I'm a computational chemist by formation, so I studied computational chemistry. I joined IBM 10 years ago in 2008, and I have been working quite extensively in the space of material design and computational material science. Since a few years, 4 years roughly, I'm starting to coordinate the activities in the space of AI applied to chemistry and materials. And the purpose of today's presentation is the one of giving you some highlights regarding IBM reaction for chemistry. That's how we pronounce this acronym. And the technology that is behind it, what you can do with this type of technology. So I'm going to start directly, and first of all, I mean, I want also to mention that I'm sort of the front person in this presentation, but there is a pretty extensive team behind it, and the name of the collaborators are all referenced in this first page. Now, when we started the activity in the space of chemistry, so trying to apply artificial intelligence technology in chemistry, this was very much driven by the fact that in chemistry there is an endless chemical space that deserves to be explored. This is true if we refer to possible molecules with drug effects, but is as well true if we refer to the complex space of chemical reactions. So this was really very much the driving force of our motivation, trying to exploit artificial intelligence and more specifically neural network type of technology for accelerating the discovery process in the space of synthetic chemistry. More specifically, the presentation and the tool that I will be showing today is related to the problem that in chemistry is called forward reaction prediction problem. So whenever you have a set of reactants and eventually with the reagent condition, the problem of forward chemical reaction prediction is the one of determining what are the most likelihood or most probable products that are going to be generated by that specific chemical reaction. So this is one part, of course, of the interesting problem in the chemical industry. There is another one, and I do have a slide at the end of the presentation that is facing the opposite problem. So given a product, what are the best reactants and reagents and conditions for synthesizing that molecule? So the inverse problem is actually very well known as a retrosynthetic problem. Again, today I will be focusing mainly on the forward reaction prediction problem. When we started the forward reaction prediction problem, one of the major ideas that we had was the one of validating an hypothesis that we were a strong believer of, that in organic chemistry, in chemistry in general, in organic chemistry in particular, there is a very specific language behind it. The grammar of this language may be incredibly complex. It's difficult probably for the human brain to master and to define with very precise rules, but there is a language underneath. And so the idea that we had in developing this artificial intelligence model was the one of treating chemistry just like a language, just as you are treating English, German, French, Italian. Now, in order to, and probably you may be aware, for instance, of a lots of artificial intelligence tools that are very useful for translating between languages. For instance, I'm living now in Switzerland since more than 10 years, and still I'm a strongly user of the technology like Google Translate, for instance, for supporting the translation between languages. So what we wanted to do was trying to develop a very similar tool in the space of chemistry, where instead of translating between languages, we are translating between reactants, reagents, conditions into possible products. It's basically what I'm lighting now. Now, the major complexity, the major obstacle we faced at the beginning of the work was the one of having access to data. Like anything in the space of artificial intelligence, you need to have data to train your model. And a similar story was in the space of chemistry. So we had to collect enough data to train then the networks and the idea that we developed in the past months. Now, we started with a work which was not made inside IBM, actually was made at the University of Cambridge by Laino during a PhD thesis. And there are actually, this is a very nice piece of work in the space of natural language processing. So this work is related to crawling through patents and extracting from textual information reaction patterns. So basically chemical reactions that are described in procedure of patents. This is really a very intensive text mining activity. The generation of these databases are actually codified as a smarts, which is a way to represent in a string information like the one that I'm depicting here at the bottom of the slides. So we started from these databases and we performed a series of cleanup operation to guarantee a certain level of quality in the initial training of the data. And finally, we ended up with a data set, which is a data set of approximately 500,000 chemical reaction, that is the chemical reaction set that is currently used by us and by different groups, including groups in MIT and other US universities, for comparing the quality and the validity of different AI models for predicting chemical reactions. Now, going back to the initial statement, that's how we decided to tackle this problem. So you think of having reactants, reagents, and conditions, and this is one first part of what we would consider a first language. And then by using the same type of technology that has been used in neuronal machine translation models, we want to predict actually products. Now, working with graphical content like the diagrammatic schemes is actually very cumbersome, very difficult for training the AI model. So we decided to rely on string representation. Basically, in this string representation, which is a notation known as miles, we are encoding each atom with basically a set of characters, either one or two. And in this context, actually, the individual characters are just like words in a sentence, and groups of words are making up sentences, just like the phrases that you have in natural languages. So we used precisely this series of string information to train a sequence-to-sequence model. That's the nature of the model. The model has been made public approximately 1 year ago. It has been presented the first time in NIPS December 2017, and all the details of the model are actually completely public, including also the testing data set that we have been using for validating the model. Now, how does it work? A sequence-to-sequence model, which is actually a specialty of a neural network. We actually do have a source, and this source is representing the input, and in our specific case, the input is nothing more than everything which is at the left of the reaction arrows. And this source and input is encoded using a specific encoder into a sort of feature space, and then everything that is in this feature space is actually decoded with a generative model that is actually creating the output of the chemical reaction. And in our case, the output is the product. So during the training, is important to go through a sort of tuning of all the layers that are here in between, the encoder, the feature space, and the decoder. And this tuning of the features is actually known as training. So what we were doing, we were using this set. I was talking before about the alpha million data set point. We have been using these alpha million data set points for actually training the intermediate part of the AI model. And doing that because the input is known, the output is also known. So you can actually, by constraining input and output, knowing which output is corresponding to which specific input, you can optimize the intermediate layer. So that's a slightly better representation in which we are also depicting a very important features, which is crucial for the entire architecture, which is an attention layer. And actually, one of the latest release of the AI model that we have in the model that is available on the web is even more simplified than the one that you can see depicted here, and is actually almost completely based on attention layers. And again, of this one, I do have at the end the references. So the articles that are preprints are already available, and people that are interested in more technical details can easily find all the question in the scientific article. Among the things that are very important to be stressed is that the entire system is fully data-driven. What does that mean? It means that we, beyond the data, the chemical data, the smiles, the strings, the reaction strings that are used for training the entire architecture, we ourselves are not injecting any additional chemical knowledge into the model per se. It's template free, so this means that we are not taking advantage of any templating chemical reactions, which is a different way of encoding chemical knowledge. And we are not even using atom mappings, which is again a very standardized trick for building chemical reaction prediction machines. The other interesting thing is that the entire system is really trained end-to-end. This means that the entire box, the entire AI model per se may be utilized even for translating between two different languages, natural languages. Actually, the same architecture, as I mentioned at the beginning, is actually very much resembling, I would say, close to 95, 98%, the same type of architectures that are used for in the context of neuronal machine translation project. And there is only a very little part that is customized to deal with molecules. And this means that the entire box, the entire AI box, could easily be exploited for building your own translation machine, your own Google Translate, for instance. And in this respect, trained end-to-end means that we really have initial data that we are using for training, and we have output that is generated, and that then is used for the training purposes.
Oh, Teo, just a moment. There's lots of excited questions in the chat, so just briefly mention them.
Sorry about that. I see the question, but I'm not monitoring the chat.
Yeah, no. I'll just stop you just for a moment, just before you go on to the data sets, because I think this is a great point. So one question is, are you doing metal organic MOFs, or is it all inorganic chemistry?
So most of the data, let me clarify something. Whether we deal with inorganic, metal-organic, or purely organic chemistry is very much connected to what type of chemical reactions we are covering with the data sets. In this specific context, we tried to cover with this data set, which is open and was one of the few that we were able to have access. We are covering mainly organic chemistry. There is a substantial part of metal-organic chemistry. There is very little minor inorganic chemistry examples.
I see. So, you know, there's a lot of praise for your work here in the chat. But another set of questions is how much is open source and how much is available on GitHub. So, as you talk about the open data sets, it'd be interesting to hear about the other.
Absolutely. So the entire models, not only the architecture. So first of all, as I mentioned, the model itself is 95 to 98% close to the neuronal machine translation that is open source. We decided to put online and open source as well the remaining part, so you can find that one. There are a bunch of links on the IBM RXN website that are pointing to that GitHub, or at least the publications where the GitHub link is then referred to. And we do also provide, so the model is there. If everybody that wants to retrain it can retrain it clearly. The data itself is open data. And beyond making all these available, so for people to play on their own, we also decided to have already a trained model available online. And that's basically the concept and the idea behind the IBM RXN website.
That's great. So we'll probably be talking with you after this call about developing the open source aspects further, but I'll let you continue now. Thank you.
Sure. So this slide is more or less resembling what we had already discussed at the beginning. So our initial, data sets for training are actually incredibly important and are probably the very first aspect that will determine the quality of the trained AI model. We realized that more or less at our expenses, because on our skin, basically, because at the beginning we used just the original data set provided by Laui and updated basically summer last year. Still, there is quite a lot of noise in that data set. And if you just use the data set for training an AI model, specifically as we did, using the analogy between natural languages, you would end up with an AI model that is performing pretty miserably. The reason for that is actually that you need to understand that if you have noisy data, if you have data that are capturing chemical reactions, organic chemical reactions that are not even meaningful because they have been extracted with some errors, then what you are basically doing is training an AI model that is learning a broken language. So it's actually very important to be consistent and use a data set of chemical reaction that has been at least minimally curated, not necessarily humanly curated, but curated based on a set of quality control and quality assurance guidelines. So that's regarding the data set. And this is basically what happens if you try to do a prediction. So what I'm showing here is actually an attention matrix. So the magnitude of what the elements that you see in these metrics is basically a measure of the importance of the prediction. And the way you can read this metric is the following. Here we have all the atoms that are in the source, so reactants and reagents. And here in the rows, basically columns, the source, and in the columns you have, and in the rows, solely you have all the atoms that are making up the product. So what happens is that starting from each atom of the reactants, you produce a prediction in the target, and you also know which atom or a group of atoms was mainly important, and that's the magnitude of this number, in determining the order of the prediction. That's again a very similar analogy to what you do when you translate from English to French, and the order of the words in English and French or in English and German is different because the syntactic nature of the languages is different. So there are specific connection of words that are determining then the right order of the sentence, of the words in the translated sentence. The same happens at the level of reactants, reagents, and products. So we do get quite a lot of information embedded in these attention matrices, which are actually capturing also some relevant aspects of the chemistry behind the chemical reaction. That's just another example on a slightly more complex system. So this is, for instance, a Buchwald-Hartwig amination. And it doesn't really matter how complex your molecules are, but basically the system is able to deal even with incredibly large molecules and generate an outcome. And together with the outcome, also the chemical information connected with the chemical reaction through the attention matrices. Now, I want to summarize here very briefly what are the very good points. So the very first thing is that, and these are really all good things. So first of all is fully data-driven. What does that mean? It means that if anybody of you listening at this webcast is actually coming with his own set of chemical reaction or his own class of chemical reaction data and wants to train his own model, that's possible. And you don't need basically any other expertise for embedding specific chemistry in the model. The model is so agnostic that actually is capturing the chemical information from the data and is making available the forward reaction prediction capabilities. We are template free. We do not have chemical knowledge incorporated in the model. We are not using atom mappings. As I mentioned, it's trained end to end. And I also showed very briefly the availability of the attention matrices, attention weights, and confidence scores. We do also have, for each prediction, a confidence level, which is not connected to the yields of the chemical reaction, but it's really more a confidence of the model, the AI model, in giving a specific result. The other interesting thing is that we did not teach the system anything related to the syntax of the smiles. So these strings here, let me just show to you, I'm going back a couple of slides. These strings here have a very precise syntax. So there are a set of rules that are used for constructing grammatically relevant smiles. And what we realized is actually that the system not only learned organic chemistry, but also was able to learn the grammar of the smiles. Actually, overall, we are generating less than 1% of the predictions that are invalid smiles. And this tells you approximately 0.5%. And this tells you that actually the system itself, by looking at all the chemical reaction, has been able to capture the essence of chemistry and also how we are representing that chemistry. Now, there are some limitations, of course, and these are very important to keep in mind. I briefly mentioned before that the quality of the training data is crucial for assessing the quality of the AI model. So this is one of the reasons why we decided to put online a trained model, just to put everybody in a position to not to have to deal with these problematics. And so my major comment for anybody that would like to retrain this type of models is always to be incredibly careful on the quality of the data that you are using for the training. The other thing is that it is very difficult at the moment to include the negative data. And the other important thing is that because of the system, the human nature of communication, we tend not to have negative data in article patents or any other type of publication. We tend always to publish as much as possible success stories. And this is a problem because in general, we need more and more data to describe negative data, which we do not have available, while instead it would be incredibly efficient the usage and the inclusion of negative data into the model. And then the other thing is, even if we are below 1%, at 0.5%, there is always the possibility that the system is predicting something that is chemically unreasonable. As we said, there is no chemical guidelines, no chemical checks. The system is just guessing. And even if it's very rare, in this 0.5% of the cases is actually probable, possible that you get predictions that do not have chemical sense. So it's always important, again, to look very critically to the outcome. Now, I want also to mention that, and this is important also for comparison with what else is out there, is that we are not the only one to work in this field. In the past 5 years, there has been really an explosion of interest in constructing models that are working on predicting chemical reaction. What is our added value? Without revising, I'm not going to revise all the works that are out there, but the added value of what we are proposing is that even if other methodologies are template free, they still need to use a lot of chemical knowledge that is embedded as atom mapping schemes, which we are not even considering because they are irrelevant for us. This makes everything, of course, a little bit more complex to set up, especially if your data is not properly atom mapped. So that was really our goal, being as much as possible disconnected from any type of chemical knowledge and provide the best state-of-the-art model. And we demonstrated that one basically with the work that we presented first in August this year at the American Chemical Society, and we are going to present an updated number at NIPS this year. So in 3 weeks, we managed basically to beat what was considered a sort of psychological wall, the 90% accuracy. And that's where we are. We are close to 91% of accuracy. And again, all these numbers that you see in these slides by different models are all numbers that are statistically meaningful because evaluated precisely on the same data set. So always look very careful when you see evaluation, because an evaluation of an AI model is a statistical evaluation. If you change the statistical sample, the numbers, of course, are subject to changes, and therefore few % of difference may not be significant.
So your time is up to you, but I'm going to leave the call, carry on and record and show the demo as well. But I'm just letting people know if they want to drop. Sure. And you do have...
I'll need really 3 minutes only for finishing, and then I will show a very short.
Thank you. And there is a small question in the chat. Can you go in reverse? Start with 2 or 3 desired results.
I do have one slide for that one, actually. So,
excellent. Okay, please proceed then. Okay.
Okay. So this is basically the 90% of accuracy, and it's also important how you are basically dividing the chemical reactions. So, for instance, the 90%, 91% of accuracy is possible if you specify to the AI model that reactants are reactants, solvent is a solvent and is not reacting actually, and then you get your products. What happens if you don't distinguish the role between reactants, solvents, catalysts? So if you don't distinguish that, I mean, we do have a margin in respect to the other works of nearly 15%. So we are very close to the 90% also there, a little bit below. This is, of course, a more difficult task because the system somehow can get fooled by the fact that you are putting a bunch of molecules into the system, and it needs also to understand and rank the relative reactivity of the molecules. What else can we do with AI models? A very simple example that for us was a very short project, an internship project, was a training model for classifying chemical reactions. So basically you give a chemical reactions and the AI system can tell you what type of chemical reaction is the one that you have been drawing. That's a very interesting and easy usage of AI models. And another one, it's about retrosynthesis. So you will hear more about retrosynthesis in the next months. And the reason is that we are just finalizing. These are still all preliminary data that we showed up in August in Boston. And we are just finalizing in these weeks all the architecture for the retrosynthesis. And these are some of the preliminary numbers. So you can see that the top one accuracy, and this is accuracy measured on an individual retrosynthetic step. So top 1% of accuracy, we are close to 54% when the baseline and the other models are approximately 20% below. The interesting thing is that this 54% is compared really one-to-one. So for us, you get a plus 1 point. So the one prediction is accurate if we are really able to reproduce precisely what the system was expecting. But as many chemists in this audience may know, actually there may be different ways of arriving at the same molecule. So we had to have a way to assess the chemical validity of a retrosynthetic step. So if we take this 54% and all the data connected to it, and we actually use the forward reaction prediction model, then we get that actually the number of retrosynthetic steps that are correctly predicted is more than 54%. It is actually 75%. Now that's, of course, is a very easy way for people that do not have organic chemists in their environment, in their working environment, to use an AI model for forward reaction prediction to assess the quality of an AI model for retrosynthetic prediction. So this is really very, very preliminary information. I sooner, either shortly before Christmas or after Christmas, we are going to have a more extended scientific publication also on this very important aspect. Everything that I mentioned is actually available online. I guess that this URL made its way. I mean, is actually very simple. AI for Chemistry is a redirection to the RXN website. On the RXN IBM.com website, you will also find some of the publication, and in this publication you find the links to the GitHub if you are interested into the open source components of the models, the training data. This is the article we recently submitted to NIPS this year, and this was the one published on Chemical Science in June, and that's more or less it about the presentation. If Susan, I do have really 2 minutes, I will just very quickly show how it works, the platform.
Please do. Yes, please do. Go ahead.
Okay, so once you go to the research IBM.com AI for Chemistry, you will be landing on this page. That's basically the landing page. You can start directly your new projects. There are different possible ways that you can use, logging with your Facebook or Google account. In this specific case, I'm going to use my Google account. And what is presented to you is basically this dashboard. The dashboard is organized with projects. I'm going basically to just create a new project, and that's the webinar 18. You can add collaborators, and once you open a new project, you end up directly with this whiteboard where you can draw your molecules. Now, I'm going to make something very simple for really only for demonstration purposes. So for instance, we may try to do something like that and go just for a very simple reaction of water with hydrocarbon. So again, it's not important. The specific reaction, you can draw there things as complex as you like. Once you have specified what you would like to have as a reactants, reagents, you can just run your prediction. What is happening at this stage is that everything you have been drawing in terms of reactants, reagents, catalyst is converted into a smile, is sent back into the backend engine. The backend engine is actually the one that is doing all the AI prediction, and you get back your best likely products together with your attention metrics. You also get a confidence level. In this case, is pretty high, close to 80%, the confidence of the modeling, the prediction. If you want, and this is something that really is left to the engagement of the people, you can give us a feedback, it's correct or is not correct. And if it's not correct, you can also tell us what you believe is actually the correct answer. Now, once you do a chemical reaction, you will find, of course, your attempts in your attempts. And here we will find actually the chemical reaction that we just drawed. You can save chemical reactions, you can share with other people, you can import molecules and do everything that you like. Eventually, you can even use the products. I can add the products of my board, and I can go on with a forward synthesis plan. So that's everything I wanted to show you. I wanted also to make few remarks that are always very important. We as IBM are not monitoring the activity on this platform. This is really a trained model that we made available freely to everybody worldwide, with the main purpose of assessing by yourself the quality of an artificial intelligence model. Be also aware of the fact that we do not have in place on this platform protocols for dealing with confidential data. So this means that although IBM is guaranteeing that we are not doing any type of monitoring, we cannot guarantee for possible loss of data. So my number one warning is always try the AI model, have a look at how it's performing with toy systems, engage other people, colleagues. I mean, have them basically use this technology, but don't put their confidential information as, again, a cloud service for storing confidential information as a cost, and basically a certain number of technologies in place that, of course, we are not covering in this freely available version. This is only a warning, and I open if there are questions.
Right. I do see a couple of questions in the chat. I think it was Jim who was asking, like, the accuracy. So what are the errors telling you when the accuracy isn't? Yes.
So we are talking about the confidence, if I understand correctly. So if the confidence is low, what does that tells you about the prediction? In general, I hope I understood correctly the question. If this was the question, I can say that in general, reactions may look correct, and actually they are correct, even if the confidence is below the 20%. The reason for that is that the confidence number is just a number that the mathematical architecture, which is behind the AI model, gives back. And it's really a measure of how confident is the model in creating that outcome based on all the other example and knowledge that the model was exposed during the training. So it's definitely, normally if the confidence is very high, you can bet that the accuracy is high. So this means that the predicted outcome is very probably correct. If the confidence is low, always be very careful, because it could be that you are asking to predict a chemical reaction for which the system saw very few examples.
Right. Okay. Understood. Thank you. And then I think there was another question. I think when you were talking about competitions,
Mm-hmm.
How fast does the top system change? Is there a big movement in these competitions, and do you have some URL so we can go and look at these?
We are talking about competitions with other models. I guess this was
Yes,
probably
I think
referred
so.
to.
Yes, I think that's.
I mean, this is more or less regarding how fast these things are changing. It's actually very. I have here basically 3 models. So this Jean et al. Is a model that was made in 2017 at MIT. Schwaller et al. This is our sequence-to-sequence model, the one that we published December last year, and Bradshaw is actually a model that came out few months ago. So in general, there is a very fast piece in producing new models. And I know, for instance, that even the MIT is coming with another model that is more or less faring at 86 to 87%.
Mm-hmm.
So it's a field which is highly evolving. There is no unique website that is collecting all this information. We tend to do normally in our article, but I'm pretty sure that the same are doing also the other authors, a comparison every time you come up with an improvement. So for instance, if you look, this is only as not for sponsoring not for sponsoring the the article, but if you look at one of our last publication here, the one that we submitted for NIPS, and again, this is openly available, so you can have a look at that one. There we have a table again where we are comparing the state-of-the-art models. The same will happen if you find a latest one. Unfortunately, there is not a unique website where all this information is gathered.
Thank you so much for the superb talk, Tia. Really enjoyed it, and so does everybody. So did everybody else. People have commented in the chat. So I'll be posting the recording later today. Your slides are already public. Thank you again for the great session.
Thanks to you, Susan. Really, it was a pleasure.
Thank you. Bye bye. Bye bye.
Bye bye.
Everybody.
Bye bye, everybody. Bye.